We have discussed the common source amplifier and many different ways of biasing it. The common source amplifier is a native use of the MOS transistor. That is, the incremental picture of a MOS transistor is this, omitting the output conductance GDS. It is by itself a voltage controlled current source. Okay. In a common source amplifier, what we do is simply connect a source to one side, signal source, and load to the other side. And of course, there can be extra components because of the way we choose to bias the transistor. But this is the basic common source amplifier. Okay. And this gives a gain which is minus GM RL. This is the output voltage. Okay. Now, there are many occasions when you need a different type of functionality. That is, this gives you a certain gain, but the gain is dependent on the load resistance, and it's of course dependent on the GM of the transistor and so on. Okay. So you may want a voltage gain that is independent of the load resistance. So regardless of what load you connect, you will get the same gain. Okay, so that's one possibility. Or you may want a voltage controlled current source just like the MOS transistor, but it shouldn't depend on GM. Like I've said before, these characteristics of semiconductor devices like GM and so on, the transconductance and other parameters depend strongly on temperature, and they also vary quite a lot from device to device. So it is useful to have something where you could still have a voltage controlled current source like the MOS transistor, but its characteristics do not depend on the transconductance, which makes it more accurate. Okay, so in short, we would like to realize other types of controlled sources. Okay, and the four types of controlled sources are a voltage controlled voltage source, a voltage controlled current source, current controlled current source, and a current controlled voltage source. Okay, so all these can be realized using a MOS transistor, although the MOS by itself looks like a voltage controlled current source whose transconductance depends on its operating point. Okay, so we will realize all these things, and in order to realize any of these things, we have to use the concept of negative feedback. Now, we are already familiar with it because we used negative feedback to bias the transistor at a given current instead of at a constant gate source voltage. Okay, we will use the same principle to realize these control sources. Okay. Now, before we go into the details of implementation, in a MOS transistor, we have three terminals: gate, drain, and source, and there is a control source between drain and source, and the value of the control source depends on the gate source voltage VGS. Okay. When we use negative feedback, what we have to do is, let's say we have to sense the difference between certain quantities and drive the output in a way such that the difference is reduced. Okay. Negative feedback means that you sense the difference between some quantities, I'll say desired and actual, and you drive the output, that is the actual output, in a way that reduces the difference. Okay. So that is negative feedback. That is, you drive the output in a way that reduces the difference between the desired and actual output. Okay. When we use a MOS transistor to do this, we have to drive, let's say, current into some load or increase or decrease the voltage at some node. Okay. That is, we have to either increase or decrease the current going into some branch, or increase or decrease the node voltage. How do we do that? The MOS transistor by itself is a current source, that is a controlled current source. We can still control voltages with it. So if you want to increase the node voltage, you have to push a current into it. Okay, this we have seen earlier. You can always imagine a parasitic capacitance and the current flowing into that parasitic capacitance, and eventually the voltage will rise. And similarly, if you have to reduce the node voltage, you pull a current out of it. Okay, and of course, if you want to change the current in some branch, you simply drive the current from the control current source through that branch. Okay, so we can either control voltage or current while we still have a controlled current source. Okay, it is possible. And also we have to sense the difference between certain quantities. What does the MOS transistor sense the difference between? It senses the gate source voltage. Okay, this we have talked about earlier. It's a unilateral device. If you want to change the value of this current source, you have to change the gate source voltage. That's the only way to do it. So somehow, whatever it is that you want to sense, it has to be translated into gate source voltage. Okay, in the appropriate direction. So when gate source voltage changes, this current changes. That's the only way to change it. When you sense the difference between desired and actual values, somehow that has to be converted into a corresponding VGS so that the drain current is changed. Okay, so you have to apply feedback control to the gate source part of it, and you will get the output from the drain source. So I hope that part is clear. Also, you can see that in a MOS transistor, the cause is applied between gate and source, and the effect appears from drain to source. Okay, so the input can go to either gate or source, and the output can come from either drain or source. Okay, we'll see examples of both. And of course, drain can only be an output. You can't apply something to the drain and expect something to happen. And gate is only an input. You can't expect anything out of the gate. Okay, no signal comes out of it. The source can be either. Okay, so the source is part of both the controlling side and the control side, and it can be either input or output. And again, we'll see examples of both of them. Now, because of the way the MOS transistor is, there are some restrictions. What I mean by that is, let's say we had some hypothetical device with 4 terminals, and the controlling and control sides were completely separate. So let's say this happened to be VGS and this was GM VGS. I'll just call these terminals 1, 2, 3 and 4. In this, it's very clear that 1 and 2 belong only to the input and 3 and 4 only to the output. And this picture also is very symmetrical. Okay. Whereas the actual MOS transistor we have, it doesn't look like this. These two are together. There is a common terminal. Okay, so that also introduces some constraint into some of the circuits that we will realize, and I'll point them out as we go along. Okay, so our goal in the next several lessons would be to realize control sources using a MOS transistor, and we will use negative feedback in order to do that. Okay.